Hi everyone. Today we're going to be doing some more work on motors and generators. We're going to be learning about the forces between two parallel wires, and we're going to be learning a bit about torque, because once we can describe torque, we're able to talk about things spinning instead of just things moving. It's a little like an analog to force, but we'll get to that in a little while. First, I'd like to cover this: the forces between parallel conductors. The thing is, we know that conductors create magnetic fields. And we know that conductors in magnetic fields experience a force if they're perpendicular to that field. So if we have two wires very close together, one of them will create a magnetic field, and it will make the other one experience a force. So let's figure out just how that works. So we know that when a conductor carries an electric current, it produces a circular magnetic field, like we can see in these diagrams. In a magnet, the field lines go from the North Pole to the South Pole, but for conductors, the field lines are circular, so they don't have a starting point or an ending point. So when two parallel current-carrying conductors get close to each other, their magnetic fields will interact. And in fact, because they're conductors in a magnetic field, it will cause each conductor to experience a force. So how exactly will this force act? That is, how will the magnetic fields interact with the conductors? Well, we're going to get some sort of motor effects going on. But in what direction? Well, let's take a look at the magnetic field around the conductor, right? So we'll start off with just a conductor carrying a current from left to right, right? We're going to have two parallel conductors, but we've just taken the first one. So we can draw the magnetic field around it. What will it look like? Remember that we can use the right-hand grip rule, or the right-hand curl rule, to figure out how the magnetic field goes around the conductor. Thumb points in the direction of current, thumb of the right hand, and the fingers will curl around in the direction of the magnetic field. So it means the magnetic field will come towards you at the top of the wire and away from you at the bottom of the wire. So it looks something like this, right? So we can imagine that the magnetic field lines are going in circles, right, around the conductor. As we can see, closer to the conductor, the magnetic field is strong, and further away from the conductor, the magnetic field is weak. Right? So what happens if we put another conductor in this field? Well, now we have a conductor and it's in a magnetic field, so we can use the right-hand palm rule to figure out the effects of this magnetic field on the conductor. Right? So, right-hand palm rule. Thumb points in the direction of current, fingers point in the direction of the magnetic field. Right? So that means the force on this particular conductor will be upwards toward the first conductor. So as it turns out, we can draw this sort of diagram for any two wires, and every single time, if we have the currents flowing in the same direction in both wires, then the first wire will attract the second wire. Remember, in that last diagram, the bottom wire was experiencing an upward force toward the first conductor. That's because they were both carrying current in the same direction. So what happens if they're carrying current in the opposite direction? Well, as you might have guessed, the magnetic field lines will move the other way around. So the second conductor will be repelled by the motor effect. It'll experience a downward force instead of an upward force. So the second conductor will exert the same force as the first conductor exerts on it, right? That's Newton's third law. For every action, there is an equal and opposite reaction. So if the first conductor attracts the second conductor will also attract the first conductor with an equal force. And similarly, if the two wires repel, they will repel each other with equal force. So the strength of the magnetic field will be highest very close to the conductor, right? and it will be weaker further away. So we can, in fact, figure out mathematically that the strength of the force that attracts or repels the two conductors will be proportional to the strength of the electric current and inversely proportional to the distance from the conductor, or rather the distance separating the conductors, because they're parallel. So we can say that the force per meter on the conductor is given by F over L, force per meter, I1, the current in one conductor, multiplied by I2, the current in the second conductor, divided by D, the distance between them. So if both of the currents are very large, the force per meter will be very large. If the distance between them is very small, then that will increase the force per meter between them. Right? Remember, this L is the length of the conductor, not the distance between the conductors. So what's this K over here? Well, it's a constant. It turns out that if we substitute in I1 and I2 in amperes and D in meters, then we won't get an answer that's in newtons per meters. We'll get an answer much smaller than the true value. So we need to multiply it by this constant of proportionality in order to scale up the result, or scale down the result to the force that we want. Right? So this K is a constant number. It does not change. This number K is based on a universal physical constant that doesn't change for the universe that we are in. So it will always stay the same. And it will always mean that the force per meter between these two parallel wires will be less than simply multiplying these three terms. Now, in fact, this equation here is where the definition of the ampere comes from. Remember, the amp is what we use to measure current, right? So here's how we define 1 ampere. We set up two parallel wires, right, 1 meter apart, and vary the current flowing through them, right? We can either increase the current or decrease the current. We will say, however, that the current will be exactly identical in both wires. Okay? So we have two wires with varying amounts of current flowing through them. And this means that there'll be different forces between them as well. Right? When we increase the current, the force will increase, and when we decrease the current, the force will decrease. So this is how we define the ampere. We say that when the two wires attract each other with exactly this force per meter, then that's when 1 ampere is flowing through each wire. Right? So we vary the current until this is the exact force attracting them per meter, and that means that exactly 1 ampere must be flowing through each of them. And from here we can actually see our definition of K in this equation. K is equal to 2 times 10 to the minus 7. So remember, this doesn't change. It's a universal constant that will be the same everywhere in the universe, as far as we can tell. So, if the current flowing through each conductor is in the same direction, then I2 and I1 will both be positive, or they'll both be negative, because they're the same direction, right? This means that when we multiply them together, we get a positive number. If, on the other hand, one is positive and one is negative, then when we multiply them together, we'll get a negative number. So the force per meter that we calculate with that equation is the attractive force per meter. If it's a positive number, then the two currents are attracting each other. If it's a negative number, then the two current-carrying conductors are repelling each other. Make sense? Good. Alright, so now that we know about the forces between parallel conductors, let's go on to some questions. Question 1. Two wires are in parallel. When the current in each wire is doubled, what happens to the force per meter between them? Now we can figure this out with our equation. Let's write it down. F equals constant of proportionality times I1, I2 over D. Remember, this is force per meter, so we can have the over L on the left-hand side or the times L on the right-hand side. I'm going to leave it on the left-hand side because the question asks about force per meter. So what we're doing is we're doubling I1 and we're doubling I2. So we're actually increasing the right-hand side by a factor of 4. Can you see that? So what will our answer be? That's right, the force quadruples. We double the force between them twice because we double both I1 and I2. Question 2. Two wires are in parallel. When the distance between the wire is doubled, what happens to the force per meter between them? Now think back to our equation. What's on the denominator of the fraction? Is it the square root of d? Is it just d? Is it d squared, d cubed? So that will affect the answer to this question. Now, when we increase the distance between the two wires, the magnetic field of each one that acts on the other will get smaller, right? So that means that the force is going to get smaller, not get bigger, right? And it's not going to disappear either. So is it a d on the bottom or a d squared? That's right, it's just a d on the bottom. So because the force per meter is inversely proportional to d, of I1, I2 over d, when d doubles, the force will halve. Question 3. Two wires running parallel, 1 centimeter apart, carry a current in the same direction. One wire carries a current of 1 amp, and the other carries a current that varies. Sketch a graph of the force per meter between them as the current increases from 0 to 1 amp. So let's see if we can figure this out. We know that the force equals I1 times I2 over D, right? So if one of the currents is 0, the total force per meter will also be 0, right? So we're going to start off with 0 force at 0 current. So that is, we're starting off at the origin, 0, 0. Now, when the graph increases, after we increase the current, how will it increase? Will it increase in a sort of square root pattern or a parabolic pattern? Well, we can see from our equation once again, F equals I1, I2 times a bunch of things. As I2 increases, F is going to increase proportionally, assuming all the other factors stay the same. That means that the graph will be a straight line. All we need to do now then is figure out another point on the line, and we can just draw a straight line through it. So let's look at the end point, 1 amp. If we look at this 1 amp and we put it into our equation, we can see that F over L, the force per meter, equals K, that's 2 times 10 to the minus 7, times 1 over this many meters, right? So if we replace the K with a 2 times 10 to the 7, minus 7 rather, we can substitute this into our calculator to figure out the end point of our graph. Right? Turns out to be 2 times 10 to the minus 5 newtons per meter. So with that as our end point and the origin as our start point, we can draw a simple graph that looks like this. So we can see that the force per meter goes from 0 up to 2 times 10 to the minus 5 as the current through the second wire increases from 0 to 1. And that means that we just have this lovely little straight line graph here. So the end point matches up with those numbers. Make sure that you title the graph and you label your axes. It's very important to leave the units in as well. So the force per meter is in newtons, force per meter, and the current is in amperes, just like the question says. Question 4. Consider the three current carrying conductors shown. What is the direction of the net force on wire Y? That is, this wire. Now, can you remember how parallel currents attract or repel each other? That's right, if the current through two wires is the same, that is, if it's in the same direction, then the two wires will attract each other. But if the two currents are in the opposite direction, the two wires will repel each other. Right? So we can write that down here. Now let's look at the different forces on the wires. X and Y will attract each other, right? Because they both have current moving this way. So there'll be a little bit of force going that way for each one. How about Z and Y? These are carrying currents in the opposite direction. Z is carrying it towards you, Y is carrying it away from you. So these two will repel. And there'll be a little bit of repulsive force going like that. Now to find the net force on Y, all we need to do is add these two force vectors up, right? And we can see that once we do that, the net force on Y will be in that direction, because we've added these two smaller force vectors together. Remember that vectors are added together by putting them down next to each other, head to tail. So in this case, we'd be adding the vectors together like that. Right? Makes sense. Question 5, a quantitative question. What is the electromagnetic force per meter on a long wire if it carries half 1 ampere of current in a 0.01 Tesla magnetic field perpendicular to the direction of current flow? Now you might notice that this is not a question about parallel conductors. It's a question about the motor effect, that is, a current carrying conductor in a magnetic field. Can you remember the equation that we used for that? That's right. F equals BIL sine theta. Now we know that our wire is going to be perpendicular to the magnetic field, which means that sine theta is going to equal 1. So it won't change the result. But we're not looking for force, are we? We're looking for force per meter. That's what the question asks. So we can divide both sides by L. Then we get an equation saying that our force per meter is simply equal to the strength of the magnetic field times the strength of the current. So let's start with that. Now all we need to do is substitute in some numbers. Our magnetic field is 10 millitesla, that is 0.01 Tesla, and our current is half 1 ampere. So we substitute those in, and that gives us a value of 5 times 10 to the minus 3 newtons per meter. Because remember, we don't have a force, we have a force per meter. Part B. What is the force per meter exerted on the first wire by a second parallel wire that also carries 0.5 amps and is at a distance of 1 centimeter from our first wire? So in this case, we use the familiar equation that we've learned. F over L equals the constant times I1, I2 over D. Now we substitute in the numbers. We have 0.5 amps in each. We have a distance of 1 centimeter. So substituting those in, our force per meter can be found out with a calculator. Turns out to be 5 times 10 to the minus 6 newtons per meter. So now we have an answer for part B and for part A. And both of these will be important for part C, so I'll just put them up at the top of the screen. Compare the effects of these forces on the wire. So the magnetic field force, that is, the force that the current felt when it's in the magnetic field, is 5 times 10 to the minus 3 newtons per meter, whereas the force that it felt due to the other conductor was 5 times 10 to the minus 6 newtons per meter. Now, how did these two numbers vary? Well, look at the relative strength between them. This is 10 to the minus 3, but this is 10 to the minus 6. So how many times bigger is this number than this number? Well, that's just indices, right? We take 10 to the minus 3 divided by 10 to the minus 6, and to answer this, we take the minus 3 and we subtract negative 6, which is the same, of course, as adding 6. So we end up with 10 to the 3. That means that the magnetic field force is 1,000 times larger than the parallel current force, right? And if it's 1,000 times larger than the parallel current force, then how is it going to affect the wire? Well, we can see that the force due to the magnetic field is many times stronger than the force due to the parallel wire. So the effects of this magnetic field on the wire are going to be much, much stronger than the effect of the parallel wire. Even if the magnetic field was 10 times weaker, the effect on the wire would still be 100 times more than the effect due to the parallel wire. So that's the end of the questions. So we've learned about current carrying conductors attracting or repelling each other based on the strength of the current and the distance between them. In the next section, we'll be looking at something completely different. We'll be looking at torque. Torque is a little bit like an analog to force, but instead of causing movement, it causes rotation. More on that in the next section.